In this video, we are going to see dual cycle derivation and problems. Myself, Rajkumar, Assistant Professor, Department of Mechanical Engineering, Rohini College of Engineering and Technology. Dual cycle is the air standard cycle, which is a combination of thermodynamics Otto cycle and diesel cycle. The thermodynamics power cycle consists of two constant volume process, two adiabatic process, and one isobaric process, that is constant process. Here you can see this PV and TS diagram. The first diagram is the PV diagram. There is 1 to 2 is the uh, adiabatic process, and 2 to 3 is the constant volume heat addition process, and 3 to 4 also heat addition process with respect to constant pressure process, and 4 to 5 equal adiabatic expansion process, and 5 to 1 is a constant volume heat rejection process. Then the expression for the air standard efficiency of the diesel cycle, it is seen the efficiency decreases as the value of density increases, and therefore it is desirable to keep the value of rho, that is as small as possible, to increase the efficiency. This can be done by supplying the heat partly at constant volume and partially at constant pressure. In actually oil engine working on this cycle, it is obtained by injecting part of the fuel towards the end of the compression stroke. From this diagram, the air is compressed isentropically from a condition 1 to 2. The heat is supplied to the compressed air partially at constant volume and partially at constant pressure until the air reaches to the condition 4. The air expands isentropically until it's reached to the condition 5. The heat is ejected by the air to the external sink at constant volume until it reaches to the condition 1 and the cycle repeated. In actual practice, the engine operates on open cycle and the heat is supplied by injection and burning of fuel. The condition 5 is the condition burned gases and they cannot be used again, and the fresh air is taken from the outside from the next cycle. Such cycle is known as dual cycle or mixed cycle. This cycle has the advantages of both Otto and diesel cycle. The work done by the cycle per kg of air and the air standard efficiency of the cycle can be calculated in these equations. The heat supplied during the process 2 to 3 and 3 to 4 is heat supply Qs equal to Cv into T3 minus T2 plus Cp into T4 minus T3. That is, Cv means specific heat at constant volume and Cp in this specific heat at constant pressure. The heat rejection during the process 5 to 1 is Qr equal to Cv into T5 minus T1. Then the work done is W equal to Qs minus Qr, that is Cv into T3 minus T2 plus Cp into T4 minus T3 minus Cv into T5 minus T1. That is, finally the efficiency formula equal to eta equal to work done divided by heat supply. Work done, we know the value of the Qs minus Qr and divided by Qs value. Finally, we got the efficiency value eta equal to 1 minus T5 divided minus T1 divided by T3 minus T2 plus gamma into T4 minus T3, where gamma equal to Cp by Cv we know. Then the compression ratio RC equal to V1 by V2, that is V1 equal to Vs plus Vc, then V2 equal to Vc. Then pressure ratio, that is alpha equal to P3 by P2, then cutoff ratio rho, that is V4 by V3, and expansion ratio Re equal to V5 by V4. Then RC divided by Re equal to V1 by V2, that is a V4 by V5 equal to V4 by V2 equal to V4 by V3 equal to rho, or Re equal to RC divided by rho. All the temperature in the equation, then the exposed in the temperature T1, the lowest operation temperature of the cycle, that is applying the isentropic law of the point 1 and 2, T2 equal to T1 into V1 divided by V2 the whole raised to gamma minus 1. From this equation we know V1 by V2 equal to RC, that is therefore T1 into RC the whole raised to gamma minus 1. Applying the gas law to the point 2 and 3 and noting V3 equal to V2. then equal to P3 by T3 equal to P2 by T2. Therefore the T3 equal to T2 into P3 by P2. We know the P3 by P2 is equal to RC the whole raised to gamma minus 1. So finally we get T3 equal to T1 into RC the whole raised to gamma minus 1 into alpha. Applying the gas law to the point 3 and 4 and noting P4 equal to P3. Therefore V4 by T4 equal to V3 by T3. From this equation T4 equal to T3 into V4 by V3. We know that T3 equal to T1 into RC the whole raised to gamma minus 1 into alpha into rho. Applying the isentropic law to the point 4 and 5, T5 equal to T4 into V4 by V5 the whole raised to gamma minus 1. Here the T4 equal to T1 into RC the whole raised to gamma minus 1 the alpha rho 1 by RE the whole raised to gamma minus 1. That is T1 into RC the whole raised to gamma minus 1 into alpha rho divided by RC the whole raised to gamma minus 1 equal to T1 into alpha rho the whole raised to gamma. Substituting the value of T2, T3, T4 and T5 in the equations, the equation we get finally the efficiency neta equal to 1 minus T1 into alpha rho the whole raised to gamma divided by minus T1 divided by T1 into RC the whole raised to gamma minus 1 alpha minus T1 into RC the whole raised to gamma minus 1 plus gamma into T1 into RC the whole raised to gamma minus 1 the alpha rho minus T1 into RC the whole raised to gamma minus 1 into alpha equal to neta equal to finally we get the efficiency for dual cycle equal to 1 minus 1 divided by RC in the whole raised to gamma minus 1 into alpha rho the whole power gamma minus 1 divided by alpha minus 1 plus gamma into alpha the rho minus 1. This is the dual cycle efficiency. Next we are going to see the problem related to dual cycle. An air standard dual cycle has a combustion ratio of 10. The pressure and temperature at the beginning of the compressing are 1 bar and 27 degrees centigrade. The temperature after constant volume heat addition is 987 degrees centigrade and the net heat supplied to the cycle is 878 kilojoule per kilogram. What will be the cutoff ratio of the cycle? So you can see first of all you just draw the PV diagram for the dual cycle. Then only you can find out the data of the given problem. So first of all read the problem. First compression ratio, that is a R value equal to 10. Then pressure and temperature of the beginning of the compression is P1 value and T1 value. P1 value equal to 1 bar and T1 equal to 27 degrees centigrade. So converted into Kelvin. Then the temperature at the after the constant volume, the heat addition is, that is Q is heat addition is 987 degrees centigrade. 987 degrees centigrade means the temperature, that is a T3 value is 987 degrees centigrade. That is we are going to convert it into Kelvin, and the net heat supplied to the cycle Q equal to 878 kilojoule per kilogram. Then we are going to see the cutoff ratio of the cycle. First of all, heat supply. We know the value Q equal to Cv into T3 minus T2 plus Cp into T4 minus T3. We know some of the values only. So find out the remaining value. First of all, TV relation. We are taking the PVT relation. From this PVT relation, T2 by T1 equal to V2 by V1 the whole raised to gamma minus 1. We know the value of the compression ratio. From this we have to find out the T2 value. So finally we got the T2 value equal to 753.57 Kelvin. Now the equation, substitute the equation 1. We know all the value. Q value we know, T3 value we know. Finally we find out the T4 value. So T4 value is 1499.84 degrees centigrade converted into Kelvin. Plus 273 means we can convert it into Kelvin. Then cutoff ratio equal to RC equal to V4 by V3. So here we know the T4 value and T3 value. From this we have to find out the cutoff ratio, that is RC equal to where 1.407. This is the problem. They are asking the only cutoff value, that is a rho C. the value, final value answer is 1.407. Thank you.